Hello, greetings from Cambridge, UK. My name is Jessica Rowbury. I'm the editor of Electro Optics, and I'm here to welcome you to the first in a series of webcasts covering the shortlisted technologies from April's The Laser World of Photonics Innovation Award, which was sponsored by Electro Optics. This webinar features the shortlist from the Lasers and Optoelectronics category.
Hello, everyone, and thank you, Jess, for that warm introduction. So I'm very happy to be here today to talk to you about photonic quantum sensing at IDQ. And what I'll do is I'll briefly talk about why we do what we do, introduce you to some of the principles of superconducting nanowire single photon detectors for those of you who aren't aware. And as well, I'll talk to you about our ultra-fast and photon number resolving SNSPDs, for which we were lucky enough to win the Quantum Technologies Innovation Award at Laser Munich just a few weeks ago. We have what's known as our range of photonic sensing solutions. These include semiconductor devices, the single photon avalanche detectors, or SPADs. We also sell the time taggers, the thing which turn the electronic pulses coming out of the detectors into digital machine-readable data. We sell some very nice pulsed lasers, but the tour de force of our product range is really the SNSPD, the superconducting nanowire single photon detector. These things are really sci-fi stuff, and they're quite impressive. They weren't around a few years ago when I was doing my PhD. Well, they were around, but not nearly to this degree of performance, and I'm thoroughly jealous. There are two challenges that all of these single photon detectors face, which is, first and foremost, there's something called the photon pile-up effect, which is that single photon, single pixel detectors need a finite time to reset, and the brighter your single photon signal is, the more likely that a photon will arrive in the dead time of your detector, often limiting the detector performance to detection rates in the tens of megahertz at best. This is good enough for a lab in prototyping and quantum information applications, but short of the gigahertz operation rates that you would need for real-world application. And then the second, smaller but kind of physically interesting problem is that these detectors can only detect the presence or absence of photons. You either know if you got 0 photons, or you fail to observe a photon, or you've got 10 million in some 10 picosecond interval, for example. And to address this, there's a rather innovative solution in the parallel pixel designs of our ID281 superconducting nanowire series range. And what happens here is that several devices are connected electrically in parallel to a single readout circuit. And the advantages here are manifold. First of all, you have single photons are much less likely to pile up at 1 pixel. Secondly, smaller lengths of nanowire have a kind of smaller resistance, a smaller time constant, which means that the subpixels recover faster than one larger pixel. And thirdly, and interestingly for the physicists out there, is that the amplitude of the output pulse scales with the number of photons absorbed in a single detection. So we sell 4 or 8 pixel detectors. So you see a pulse which is proportional to 1, 2, 3, 4, up to the number of pixels, as I'll show you in a second. We're still able to achieve pretty impressive detection efficiencies, routinely above 80% for our 4 pixel detectors. And as I said, we currently sell 4 pixel and 8 pixel SNSPDs with up to 16 such detectors in a single system, which means that in a single detector, you can discriminate up to 8 photon states in a single detector.
What I want to present today is called VIBO, and VIBO actually stands for VCSEL with integrated backside optics. So this is our newest technology platform, what we have developed, and to give you a short introduction why we've moved to this technique here on the slide. So there's a big disruptive trend going on in the silicon industry, and this trend is called 3D integration. And 3D integration basically means a decentralization of the single chip. So there's not one single CMOS chip anymore, but it's spread up into multiple single chiplets, and they are stacked on top of each other. So you can have your logic and your DRAM, for example, very stacked on top of each other. And they're all connected by so-called microbombs or micropillars. And it's a full 3D integration stack. On the left side, you can see the cavity, so the two mirrors stacked on top of each other, and the surface emission. And this is actually a very compact form of building a laser device. And what you can also do, you can scale it quite easily. So either horizontally, as you can see in the center image, they're simply building up an array and making the power larger and larger by simply adding more devices. On the right side, there's a vertical stack of different junctions. So it's like a quantum cascade where you get out multiple photons of one electron. And the biggest benefit of this VCSEL technology is really that you can fabricate it quite easily on a 6-inch gallium arsenide wafers with standard silicon process technology. So you don't need to do anything fancy like cleaving the devices before testing it. And this makes it very easy to fabricate it in high volumes and get good yields out of it. And what we have done now, we combined this VCSEL technology with a more advanced state-of-the-art silicon packaging technology and create this VIBO device, so VCSEL integrated backside optics. To conclude this whole technology platform, so we are able to use advanced optical concepts by the integrated optics on the backside of a VCSEL chip. The whole device can be inherently eye-safe by design. So even if you have it in a car and a LiDAR sensor, you can be sure during an accident that the optics do not delaminate and the device will emit the same power as it has been designed for. And in general, the overall performance is very attractive for automotive LiDAR because you can do some scanning and turn on different zones. You can have a compact chip and even create a good brilliance of the device by adding a suitable optics. And due to the stacking of different tunnel junctions, for example, we can have to 100 watt per one chip. So this is also possible in a pulsed mode. And for the first time, it's also compatible to really state-of-the-art silicon packaging technology for the driver integration. So there's a link. So please feel free to have a look on the technology.